in Sukkur. And imagine, God forbid, there is a war. You know, we are at the verge of the war in India, Pakistan. What's going to happen? You're going to say, I'm going to buy my stuff and, just leave from here. How can I leave my... So what are you going to do? You're going to take the prices down actually. So no one is going to have a lot of money to, pay a lot of money for your real estate. So what you're going to sell it cheaper actually. So in other words, people take opportunities. So those who are opportunists, who know the market actually, okay, they can take risk and buy now. So when things are getting cheaper, I can buy now because I know that this thing is going to eventually go up. So people are ready to buy and sell due to several reasons. Okay. It's all this happens because of uncertainty. If you have, for example, shares of Google, they are very subtle. Okay, it's a big company, you know that they have a lot of money, so it's not going to go down quickly. Okay? But if you are investing, for example, in some kind of commodity, which commodity? Say real estate. Real estate is one form. Real estate is also pretty fluffy and real estate is not a good example. So what would be the other good example actually? Petrol constantly goes up and down basically. Gold constantly goes up and down. Okay. So all these are phenomena. Their values go up and down due to several reasons. It's all demand supply. So if things are happening due to the demand supply rule only, then this is a good model. Okay. So it doesn't incorporate the shocks actually. Shocks को incorporate नहीं करेगा model. Okay. So this is gonna work actually if things are happening due to two reasons: buying and selling. Anyways, so I would like to know this random variable, okay, as delta n h goes to 0. And in order to know the random variable, you want to estimate its distribution. And the best way to estimate, know the distribution of a random variable is to identify its characteristic function. So let's try to figure out the characteristic function of this one. By the way, do you have any intuition what distributions y is going to have roughly rough estimate? Keep in view that y at discrete time is a sum. Have you done any theorem or something that says something about the sum of the random variables? Tells you the distribution of sum of the random variables. Any theorem? Central limit theorem. So you have central limit theorem. What does it say? You have lots of random quantities. The certain assumptions. You can relax assumption IID as well. Okay. But what we did with IIDs, so we have lots of identically distributed random variables, which are basically, these are identically distributed variables. All have random distribution. Then the y is going to roughly follow normal. So you expect it to be normal. So let's see what happens. Okay, so in order to know the distribution of it, so what I would like to do, I would like to find the characteristic function of it. So what is the characteristic function of any random variable? Remember formula for the characteristic function?
E power minus
is the expectation of the exponential, okay, of looks like moment generating function. We have iota delta and y is a function of delta x. Delta is delta y delta h of
G.
This is what they characteristic function, and what I am interested in, I want to know that where this is going to go as the delta goes to. So in order to know that, what should I do? There, by the way, this lambda in R is a fixed number. So it could have any coefficient. So I treat it as a function of lambda, the function of treat it as a function of time actually. The lambda is something. Anyway, so how can I compute this expectation? In order to compute this expectation, let's take and let's try to run a kind of a heuristic argument. What we all doing today is not really very much rigorous. We're just running some kind of a heuristic argument, formal calculation. So let's take e to be, for example, n delta. Okay, e to be one of the endpoints. Then n would be, I can treat n to be velocity or delta. What would be this expectation? So expectation of exponential lambda y. I'm just writing y. We are not writing subscripts, but we have to always assume that there is delta and that's there. It's going to be equal to what? So at this time, y of t is the sum of xi's. So you have expectation of what? E to the iota lambda and sum of x's. Where I runs from 1 to n. And so I can write this as what? So I can write this sum as the product of e's, and all, since xi's are IIDs, so e to the xi's are also going to be IIDs. Okay. In other words, I can write this as what? E to the iota x1 after e to the iota lambda xn. And since x1 to xn are IIDs, so their functions are also IIDs. We did a resultant probability. So this would be equal to product of I to n exponential of e to the iota lambda xi and x is going to happen. And by the way, what would be the expectation of e to the lambda xi? So I know about xi that the probability that xi is going to take value h is 1/2 and is going to minus h also. Okay, 1/2. Okay, so this is what that is. So what would be that? E to the iota xi, so it is going to be by I equal to 1 to n. So it's going to be 1/2, but probability multiplied by the value of the function e to the iota lambda h plus
minus. Oh, sorry, plus this.
e to the minus plus 1/2 and e to the minus iota lambda h. And since this is the same for all of these xi's, so I can write it as power n. Then power n. Each of the factor has this value, this fixed value. So you are multiplying the same factor n times. So you have, and when you see this, can you see something interesting? So this is hyperbolic function. So it's cosine hyperbolic, how do we say, lambda h, okay, raised to n, okay, raised to n, And n I can write this as T over delta. If you allow this. Now, if the T and delta both goes to 0, in other words, if you want, so I wanted to take the limit of this expression. Now, this expression turns out to be this expression. So if you want to take the limit delta and h goes to 0 for this expression, what would be the outcome?
1.
The outcome is going to be that it doesn't exist actually. This doesn't exist.
Delta, you say it.
Doesn't exist. This does not exist. So can you give me a trick actually so that I can say that okay, this guy can exist. So here's the trick. Okay. Nothing is working, go for the Taylor series. In other words, I want to replace this by an expression which goes to something when I take the delta and h to 0. So let's try to approximate this. Approximation. So let me define the u to be the cos hyperbolic. Okay. As hyperbolic lambda. Is it going to be hyperbolic or cos? No, this is not going to be hyperbolic.
That's
So you have iota there. So not going to be hyperbolic. You should have remember more calculus than me. You have iota there. So, I mean, if you didn't have iota, then you're going to have hyperbolic. In other words, instead of taking the characteristic function, if you would have taken the moment generating function,
Delta is
then you would have expect to have a hyperbolic function. Okay. Cos lambda h, okay, raised to 1 over lambda. Okay. So, and take the log on both sides. What would be the log u? The log u is going to be 1 over delta log of cos lambda h.
P over delta.
Sorry?
P over delta.
P over delta. No, I'm just talking about a moment afterwards. So, in other words, whatever expression I will have, I'll just raise it to t. So if I want to substitute it here, I'll just raise it to b. So just receiving 1 over delta. Okay? So we know, so if I want to simplify this guy, so I know the Taylor series are Maclaurin approximation for cos lambda. Okay, maybe I can take, say, the first two terms. So the first two terms is 1 minus lambda square h square by 2. Okay, it's not really equal, it's approximately. Okay. And okay, for small h. In other words, if you take a small enough h, in other words, you ignore all the second order terms, that or third order terms, you're going to have certain expression. Now, so this is like log of 1 minus some small quantity. So you still have a series for it, and what is that series? So what is log of 1 minus x when x is small enough? Okay, so it is okay. Log of 1 plus x is x actually when x is small enough. Okay. So treat this as plus and as bar. So this would be approximately equal to
1 over delta.
what?
1 over delta.
Minus 1 over 2 delta and lambda square h square. Okay? And then I can do what? Let's take the handy log. So the u is going to be equal to
E power
the exponential of e minus lambda square h square over
2 delta. Okay.
Right? So therefore, what does this mean? So this means that if you compute the characteristic function of the y, this I'm finishing. Too much work. Alright, so this characteristic function e to the exponential of iota lambda y of t, okay, imagine that you have delta and h here, okay, is going to be approximately equal to u to the t. This is going to be e to the minus lambda
Square.
h square
Intercept.
2 delta
T.
yeah.
Intercept.
Lambda equal to square, lambda square,
And that's what.
lambda square h n. Now, we pretty much simplified. So if I take, for example, h and t both, say,
Zero.
h and t. If I take h and t both goes to 0, still it suffers with the same problem. We're going to have 0 by 0. What does it mean?
Sir, but H is higher, right?
H has,
Higher power. So
so
that will be
h has,
H is higher.
so
Diverges with higher rate.
so
So which would be e power minus negative infinity.
So you're gonna get 0. Yes. So in other words, you are saying that the built-in was quadratically
I know zero.
okay, fine. But what we can do is another thing. Agree with me? But let's take h square. Let's assume that h and delta are related. Each on a bigger interval, you expect a bigger change to it. But if you want to see, for example, so you check the stock of a price, okay, at 9 a.m., then you again check at, 1 past 9 a.m. So after 1 minute, so what would you expect? So in 1 minute, you don't expect to shoot actually up and down unless that 1 minute is a crucial minute.
Then you ask.
Something like that. Okay. So if the normal conditions are normal, you don't expect too much change in it. In other words, if I assume a relationship between h and delta in such a way that, for example, the h square is delta, so if I assume, I can work it without assuming it as well. Actually. Okay, but if I assume this that okay, maybe h and delta are kind of related in this manner, okay, then what will be this expression? So this expression is going to have
E power minus
more
lambda.
meaningful expression, which is going to be e to the minus lambda square. Okay.
Times T over T.
Times
T by T.
over 2. Okay. And so this is, if you have it, and hence if h and delta goes to 0, or one of them goes to 0 since they are related, then this expectation is going to be this e to the minus lambda square by 2 over 2x. Now here's the interesting question. Do you know this is the characteristic function of what? This, such kind of expression is a characteristic function of a standard model. Standard model. Do you remember, okay, that if x is normally distributed, closely related with mu and sigma square, what is the moment generating function of So e to the mu t plus sigma square over 2. Okay. So you have a very particular case of it. So let's take mu to 0 and t to the 1. We have something like this. So, we have something like this. So we are talking about, so in other words, roughly what we saw is that in these y's, as per expectation from the central limit theorem or the intuition from central limit theorem are normally distributed. Okay? They are normally distributed. I would like to put all these calculations in the form of a theorem. Okay, so what we have just done, essentially, we have proved the theorem. It simply says that consider you have this random walk. Okay. Starting from 0. Starting from 0. And satisfies all these properties. And assume yeah, right with jumps h and minus h equally likely. Okay, with the jumps h equally likely at times delta, 2 delta, 3 delta, and so on and so forth. And the final piece of assumption is the relationship between jump and the h, the time and this jump size, and assume that h square is delta, then for each, in other words, at each time t bigger than or equal to 0, this process limit delta goes to 0, y delta h of t, which I am giving a name b of t. Okay, this guy exists in distribution. Okay, an existence in distribution means what? That its expectations exist. So, the phi, think about it. If the characteristic function exists, then that means that you can compute all moments and any moment you want, any finite moment you want. And moreover, expectation of the speed, the iota lambda b of t is equal to minus lambda square dy. Okay, so that's what so far we have shown. Okay, this is what so far we have shown. So why we have taken all this hassle? Why we have taken all this hassle? Now I would like to say that we have constructed, pretty constructed but defined actually. The construction is much more sophisticated. So we have kind of defined our constructed process b of t which is defined in the terms of the random walk. So this b of t has a lot of interesting properties. By the way, I am giving this limit a name b of t. Okay, I'm giving this limit a name b of t. In other words, this limit is the limit in the sense of the distribution sum. Okay? So I'm giving this limit a name, P of t, because if you have such kind of an expression which is depending on t and delta and h, then everything else will go away except t actually. See? So if y is a function of t and delta and h, and delta and h are related, and delta goes to 0, therefore h goes to 0. So the only thing that is going to remain is T(h). And this limit exists from here, from all this analysis. And I'm giving this limit a name P of t. And I know that's characteristic function of this limit P of t. Now I would like to take some of the properties of this P of t. Interesting. Move on. Number one. It had this process P of t has finite quadratic variations. So that's the first problem. Finite quadratic variations. Okay?